All right, am I on? I think I'm on. Okay, let's do this. Hey folks, welcome back to part 6 of my thing where I'm making a Tetris data extractor. And normally I'd start this off with playing some Tetris, but I went and formatted my computer and I don't have the emulator on it. Ever since I got the CRT television and I play the real Nintendo on the real TV, playing on the computer itself is kind of meaningless, so I didn't bother putting it back. But that's okay. You could pretend that I play Tetris. Anyway, last time we had figured out a way to take a digit, say the number 1, and shrink all the black pixels, shrink it so that the edges were not non-black. And if you have no idea what I'm talking about, this is what I'm talking about. We'll see in a minute. So let's do this. Actually, test digit recognition. So these are the kinds of pictures we were starting out with. Like here's the number 0, and last time we shrunk the box until the 0 filled the entire box. And we did that, if I can try and find it here. All of my stuff is in different places since I formatted. Digit recognition tests. Bin debug. We'll open it in Paint, sure. Wait a second. Reduced image, here we go. There's a 7. It's been reduced. Oops. So you can see that 7 takes the entire bounds of the box. We sort of took away all the excess stuff, and that's what we're going to do. So the first thing I should mention, by doing that, we're going to be able to compare a new digit with a pre-existing digit. We should be able to see something match here. That's the hope. I've tried various things and nothing seems to be working, but we'll give it another shot today. So the first thing I need to do is I need to come up with canonical images for each of the canonical reduced images. I think that's the terminology we used. So we're going all over the place here. Reduced image, yeah. Okay, so what I'm going to do is I'm going to run tests in order to create canonically reduced images. And then we're going to save all those images into a folder. And those will be our canonical images. And that's just going to... that's what's going to happen. So let me... first of all, make under digit recognition, we'll make a new folder and we'll call them reduced images. Okay. Now by running, we were able to create a reduced image here by running this get digit in our tests. Oh yeah, so we took the 7, which was in our test images. We got the digit, and just for the sake of our test here, we just getting the image just reduced it and spit it out into a file. And that's what we're going to do. I'm going to do this. We're just going to do this one by one, I guess. Well, maybe not. Maybe. No, let's do this all in one go. We will do this. Bear with me. I'm just making this easier for myself. We're going to make a new directory called, well, we're just going to do this. Void reduce image. And then we're going to give it a bitmap. Again, this is going to be our digit that's not reduced, and we are going to reduce the image. Oh, my equipment's a bit wonky here. Okay, reduced image equals, this is going to be the same as we did up there. Reduce the image of the bitmap. It's going to go through the reduction. If I spell this right, that would be helpful. And then I'm going to save this. And again, I didn't spell that right, so I can rename both in one go. You might be thinking, what in the heck are you doing? Reduce image, why? Oh, whatever, public. I don't care. This method isn't being used except for what I'm doing right now. This is in place of me writing many little programs or just doing it one by one manually. It's all good. I want to take it also an integer here, integer digit, and then I'm going to save this as reduced. You know what? We'll just yeah, we'll say reduced underscore and then the digit, and we're going to call it BMP. Interpolate that string, and that's it. It's a void. We don't have to return anything. This isn't part of our interface, this method, but that's okay because the tests don't use the interface. It uses the class directly. So what I can say is, in the same way we took all of these tests, I can do it like this. I can run this quote unquote test for all the digits, and we're going to take in the file name. This is the bitmap. What's the file name? Oh, yeah, right. String digit. Okay, and we'll pass along digit. That's gonna come. No. We're gonna new digit reader. That's fine. And then we're going to go reduce image public, file name, and digit, and that's going to complain at us because digit's a string. Digit's a string and it's wanting an int, and so we'll go into here and we'll change this to a string because really it doesn't matter. We'll go back, and now we're going to run this. Actually, the first thing I want to do is to go into my various canonical images as they are right now, and you notice some of them are red and some of them are white, and that's just because that's the place I took them from the screens. Whoops. So what I'm going to do is I'm actually going to edit these, and I'm going to, oh no. No. I'm going to make these white just to make things a little bit easier. Actually, this won't make things, well, it might make it a little easier. When we do the comparison, we will compare white pixels instead of non-black pixels. I don't know. Whatever. It looks better this way, I think. So this is really exciting. Thanks for tuning in. You're watching me use the fill bucket thing in Paint, and yes, I'm closing the program every time. I'm not sure why, but it's all good. There we go. So now we're going to run our test in order to reduce these things, and yeah, we'll shove them where they belong in these reduced images directory. So let's start that. I'm going to increase this a little bit. Okay, so this is going to reduce it and call it reduced underscore and then the digit we've assigned. So let's go ahead, let's run these things. Run tests, and we will wait. I'm not sure why I... Okay, did it work? I don't know. I have a green check mark. What is this little guy? Inline temporary variable. Wow, these new versions of Visual Studio are kind of... they suggest all manner of things. Okay, let's go and look at our source. And this should be in the tests project under the bin debug. Look at that, we've got reduced 0 through 9. I'm gonna just copy them right now without even looking at them. We're gonna go into Tetris data extractor under digit recognition, under reduced images, and we're gonna paste them all. Let's look at them. I want to see them. Large icons. That is not really what I wanted. I mean, yes, it is good, but why are they red? Okay, I guess it didn't pick up my changes. I don't know why that happened. Whatever. Whatever. As you can see, here are the reduced images. It worked. Okay, so we've got reduced images, and those are all fine. We can get rid of this public method. That's not real anymore. Okay, so we are actually now, we want to fill out this get digit method. So the idea is that we're being given a bitmap, and we're gonna have to do a few things. Eventually we'll need to convert it to black and white and resize it and all that stuff, but again, we're just still dealing with the ideal case. So they're both going to be 45 by 39 or whatever they are by now, in their pre-reduced form. But in their reduced form, they're actually all sorts of different sizes, you can see. Does this actually open it? Oh. And I closed my folder. Yeah, you could. Here we go. In here, in here, in here. Ugh. Okay. You can see that, you know, the 1 is going to be narrower than, say, the 8, the 9. But a lot of them are going to be the same size, and so that's good. But we have to figure out how to deal with the different sizes. And so here's my thought. If I can get maybe here's a digit, and here's possibly another digit, this insert from a movie I bought. Okay, so these are two digits that I want to compare, and my thought is I will overlay them and count how many pixels they have in common. Now, one might be a different size than the other, and in that case, I'm going to position it in every possible way. Come on, every possible way, and count all the pixels that they have in common. And I'll find the place, and I'll just take the maximum number of pixels they have in common, and I'm just going to treat that as you know, the position that most closely aligns two images together. And I'm going to do that for all the digits. So you give me a single digit, and I'm going to check all the digits, and I'm going to make this probability chart. And there's only 10 digits. It's not going to take long. If there was an entire alphabet and various, other characters for grammar like periods and commas and semicolons and asterisks and all that stuff, I mean, that would take a lot longer. But because we've only got 10 possibilities, we know the digit is one of these things, and so it shouldn't be too difficult. And actually, as I'm looking at this, most of these are going to be the same dimensions. It's not going to take long. We're not going to have to slide the images over each other very much, because the idea is that if you've got this situation, you need to check everything. But if this was like the same width as this, pretend these are the same width, then all I have to do is check sliding the one down, up and down. I don't have to go side to side. But the weird one will be if, oh gosh, I don't even have anything. Something that's longer but shorter, then I'm going to have to slide them both around, but that's okay, whatever. Again, it's not going to be too difficult. But I do want to get this. That's my goal today, is to actually build out this algorithm. So what we've got is we've got the reduced image method that reduces an image by using these private methods that we were able to construct last time. But this isn't the algorithm. So all we do is we reduce the image. So what we're going to do is we're going to have all the given an image, I need to reduce it. So that's okay. So var reduced image equals reduce image bitmap, and that's good. I mean, boom, now I have a reduced image. Now I can compare it with all the other ones. So the idea is that I need to open up each reduced image, canonical image, in succession, do the algorithm, come up with a number, and then after I'm done all of that, return the maximum, the digit that gave me the maximum likeness to my provided image. So I am going to say, yeah, we're just going to do this. We're going to start with 0, and we're going to go up until we get to 9. And then we're going to have a dictionary. Actually, you know what? Let's just var probabilities equals get probability dictionary. And I think that's going to be okay. And by giving it not the bitmap, but the reduced image. Okay. And we're going to make this method. And this is going to actually return us a dictionary ints, and depending on what I want the map, like the measure of these things. So recall in our first way we did it, we counted black pixels and we took a percentage, so we needed a double. But now I'm going to be counting pixels that are the same, and I'm not quite sure if I'm going to subtract pixels that are different, or maybe subtract 0.5 for every pixel that's different. I'm not sure. We're going to have to tweak the values a bit, but my gut tells me I'm going to need some kind of like a decimal value here. So we're going to do that. I might have 0.5s or whatever. It's all good. And then once I have this dictionary, then I'm going to return return probabilities. Come on. Probabilities dot max and dot key, and the key is integer, so we will just do this, interpolate it. So I think that will max over the value. There we go. Max. I'm actually not I actually don't know. I'm not sure if that's going to actually tell me the maximum value in my dictionary. No, you know, let's just make this a tuple. I don't need a dictionary. Let's just make it a tuple. A tuple is just two values that are tied together. And then I can say, yeah, it doesn't have a list of tuples. Here we go, list of tuples, there'll be 10 of them. Then we can say, get me the max tuple based on item 2. Item 1. No, that's not gonna work. Here, you know what? We'll order by descending x dot item 2, and then we'll take the first one. The first one's item 1. That'll work. That'll work. So we'll take all the tuples and we'll put them in descending orders. The biggest one is at the top. Biggest is defined by it only looks at the second item. Then we'll take the first result and take the first item, which is the digit itself. That'll work. Trust me. Okay, so that's fine. That's in a nutshell. Now we have to build out this probability dictionary. We should probably change this to get let's just call it get probability. Man, that's a hard word to spell. Probability list. Okay. And now we will build this up. So probabilities equals new list tuple against decimal. Okay, and then for int I equals 0, we'll start at 0 and we'll up to and including 9, and we will carry on our way. Now we have a digit. We're going to check our reduced image against first 0, then 1, then 2. So get probability for I will say reduced image and I, and there we go. We will say probability equals, and then probabilities dot add tuple dot create, and we're going to say I is the first item, and the second item is the probability that we actually got back from our check. Okay, and so that's fine. That'll work. And then we will return probabilities. And this is how you do it. You just build up, you start at the high level, then we get the probability list, you keep going down, and now This still doesn't work because the kernel, the core of this algorithm hasn't been created yet. But we've reduced it from finding the probabilities of any digit to what is the probability that this image is this digit. So we will go get our canonical image, and we are going to open that file, I think. No, bitmap. And I think I can do digit recognition. You know what? Let's just say get file name. I'm doing a lot of methods, and that's not a bad thing. It breaks things down. So the thing is, we might want to run this on different operating systems, and on Windows you use the backslash to denote the directories separation. In Unix systems you use the /, and so .NET has a path.combine, so we're going to use that. And this, whatever operating system it's running on, will combine these into the proper operating system specific path. So we got digit recognition. That's the first part. The second part is reduced images. And then the third part is reduced underscore and then the digit itself. No, the digit itself. Yes, I haven't made that yet because I called that I. There we go. No, this needs to be a string. That's what we want. So here we go. We're going to get the canonical image. And then we are going to start getting the probability. So get, okay, this will return a decimal. Okay. And then we will return get probability. That the reduced image is the canonical image. There we go. So we're returning that. Now we've got ourselves another thing. So now we've reduced the issue. We've stripped away all of that extra stuff, and now we have 2 bitmaps. Now we can actually do our algorithm. And so the thing is, one needs to, it's possible something needs to slide, right? And so I think what's going to happen is the smaller one will slide and the bigger one will stay stationary. So just want to make sure I'm recording and not really talking to myself for no particular reason. There we go. So we're going to have to figure out which one is smaller, and they're going to be dimension specific. So the one that's smaller in the X direction is not necessarily the one that's smaller in the Y direction. This is to allow for fuzziness in the future when we take real screenshots of real games, and there's going to be stray pixels, there's going to be all sorts of things that are weird, and we're gonna try and strip that all away, but we have to allow for it. Our ideal canonical images made from emulator screenshots are pixel perfect, and they're crisp and they're clear, and that's why they're all the same size. But when we call the reduce on an actual screenshot of a really low resolution Nintendo, they're not all going to be the same size. So we have to figure this out. Okay, so, but first I'm gonna pause. Okay, I am back. So, we need to figure out which one is going to slide and which one is going to stay stationary. So we're gonna use new variables, and we're gonna say, we're going to call this, this will be the one that moves. Nope, this will be the bigger one. We're going to call it big width, bigger width, and that's going to be the reduced image dot width is greater than canonical image dot width. Then it's the reduced image. Otherwise, it's the canonical image. Okay, so this, if you've never seen this before, this is a shorthand if statement. We'll bring this here. So if this is true, use this, otherwise use this. So the bigger width is the one with the bigger width, and if they're both the same width, it'll be the canonical image. It doesn't really matter. Similarly, we're going to say the bigger height is reduced image dot height. No. Height greater than canonical image dot height. Then do the reduced image, otherwise the canonical image. And I keep spelling things wrong. Okay. So we've got the bigger one, and the littler one is going to slide. And I might change this if it makes sense as we continue. Okay. So, 4. Now we've got the smaller one is going to slide, but I need to know the difference between the widths. Okay, so width difference, do I really need to do this? I think so. Reduced image dot width minus canonical image dot width. We'll take the absolute value of that just because we don't know which one is bigger. I feel like this is going to be helpful. Height minus canonical image dot height. Okay, so we have a height difference. Now we're going to do the sliding. So we're going to go for, and we're going to call this x. Whoops. Int x equals, we're going to start at 0, and we're going to slide it along the width, the difference in the width. Okay, and every time we'll add 1 to x. And then we will do the same thing in the y direction. Y is less than height difference. Add 1 to y. So these x's and y's are going to crawl the space of the two images. Now the smaller one, you know what, we really need to figure out which one is the smaller one as well. Okay, let's turn these into your standard if statement. if reduced width is greater than the canonical width. Let's go. Big width. Bigger width. These are bitmaps. Okay. Bitmap smaller width equals null. Bitmap bigger height equals null, and bitmap bigger width. No. Oh my word. Smaller width equals null, and I totally spelled this with a capital. That's not allowed. Okay, so now we're going to set these properly. We got to get it done. So if the reduced image is fatter, then bigger width equals reduced image. Smaller width equals canonical image. Oh, you know what, you guys? I could do this so much nicer. Here. Images equals. Let's put these into an array. And then I can use link to get these properly. So we var bigger width equals images dot order by descending width dot first. Smaller width equals images order by descending x width last. Okay, so now we can copy that and paste that. Bigger height. Now this is going to be the thing that runs many times. So we may need to tweak this aspect of it. Smaller height. Since I'm doing a bunch of link statements again and again and again, which aren't necessarily very quick, but we can figure that out. So actually, let's do this. Tag or tag images or find images, whatever. We're gonna say out bitmap bigger width, out bitmap smaller width, out bitmap bigger height, and out bitmap smaller height. Okay, we'll do that. Then we can take all of these and kill that, find images. So this will find them, and we can actually take that there. This will find them, and then here we'll just call that method. And then if we need to fix it, this is the only thing that needs fixing. Actually, I do need to pass in my reduced image and canonical. And that's gonna be fine, I think. Reduce image. Actually, we could just call this image 1 and image 2 at this point. It separates your program out, so it lets you fix issues. When you have lots of little chunks, it helps you to fix issues and to change certain aspects of your program without getting confused. Because this method, its only purpose is to label one with the bigger width and smaller width. And if there's an issue with that, we know where in the code that it's centered in. So we don't have to go hunting for it. Unnecessary assignment. Oh no, that's fine. Okay, so we have our smaller width and bigger width and smaller height and bigger height. So now we're going to say, okay, get probability. Actually, we're going to, now we need to find the intersection of this thing. So every intersecting box will be the width of the smaller image. That's just true. If we're going to make an intersecting boxes, the box, we need to take a small image sized box out of the large image. We're going to start at 0, 0, and we're going to go up to and including the edge. You can imagine if the one was smaller, if they were different, if they were like this, my intersecting box is going to be smaller than both of them. And then I'm going to have to move it like this. Anyway, so we'll start off reduced area equals new rectangle. Or actually not the reduced area. See, at this point, you know what, we shouldn't call these canonical images and reduced images. At this point, it is just image 1. And this is image 2. One of them is bigger width and one of them is smaller width. Okay, folks, bear with me. Sometimes things take a little thought, and I can't think and talk at the same time. I want to start the X along the smaller width is always going to be 0 because I'm always going to take the smaller width image. The X for the bigger width is going to be changing based on X. So the crop area will be the width of the smaller image starting at X and the height is going to be the height of the smaller image starting at Y for the taller image. Yeah, but at this point we're using bigger width and smaller width. So it's okay. So the crop bigger width. This doesn't make sense. Because I don't know. I may have to split this into cases. Shoot. Okay, what we're gonna do, I'm gonna have to split this into case. Oops. I just can't see a way of figuring out that intersection when they're both different widths and heights. When one is bigger than the other in one direction and it's flipped in the opposite direction. The size of the intersection is always the same. It's just the starting pixel. Because it might be like this, but it might be like this. And I'm not sure. The bigger width is not necessarily the bigger height. And that's the problem. Okay, let me the bigger width. Size of crop. We could actually do this outside the bar intersection equals a new rectangle, and I can actually give it an X, a Y, a width, and a height. And I can say, we'll just do 0, 0, because really I'm only after a actually size. There's a size. A new size. What is this? Width and height. Smaller width. Dot width. No. Smaller. Yeah, width. Dot width, smaller height, dot height. That's going to be the crop intersection. I don't know if that's necessarily true. Because you can see, for instance, if it's an 8 and a 0, and the 0 is sitting at the bottom, no, I don't think I want to do that. I want to... shoot. It's complicated. Doesn't seem complicated. When you start thinking about the details, it's very complicated. Well, let's go back to basics. Let's start with the ideal. They're both the same size. They're totally not. What I want to do is I want to start with one image. And I want to get the pixel values for the image. And I want to compare them to another image's pixel. when you start off and it's like this, I want to compare 0, 0 of the larger to 0, 0 of the smaller. But when it's shifted, I want to compare 0, 0 of the larger to perhaps a non-existing pixel of the smaller. And I need to count pixels. I need to look at pixels that one has that the other doesn't have in order to calculate closeness. Otherwise, a 0 might look like an 8 if you only look at one half of it. So that's actually fine. I think what I'm going to, but I only want, okay, let's just, let's, you know, let's, okay, I have the width difference, I have the height difference. I don't know if I'm going to use this bigger and smaller width and all that crap. This is how many times I'm moving the image. So let's take the bigger one, the bigger width. Oh, okay, here we go. I want to compare two images, but give the second one an offset of the first one. So first, I'm going to check all the pixels of the bigger one. Oh yeah, here we go. Okay, so I'm going to check all the pixels of the bigger one. Then I'm going to check all the pixels of the smaller one, but I only want to check the pixels of the smaller one that I haven't checked for the pixels of the bigger one. That's it. Okay, so, okay, here we go. Here we go. Yeah, that's right. That's what I'm going to do. So we don't really need a bigger and a smaller. I don't think so. I do have a width difference. So let me, actually, yeah, I think a smaller width would work. Ah, crap, this is frustrating. Especially since I'm on camera and have been recording for the last 54 minutes. I'm not anywhere. I'm a little bit closer. It's probably one of those things where I'm going to walk away and think about it when I'm doing yard work later. Okay. The X difference and the Y difference. Can I move? Does it matter which one I move? I can start them both at 0, 0. Then I can just move the smaller one over. That's like moving the bigger one over the opposite way. See, I don't want to move it this way. I want to move it this way. All while keeping, so they're going to be pixels that only the bigger one has, pixels that only the smaller one has, and pixels that they both have. Okay. Get pixels from intersection, and this will be image 1, image 2, maybe I should call this X offset. And this should be called y offset. And I can say x offset, y offset. Get pixels from intersection. Not from intersection. This time it's from first image. Image 1, image 2. X offset. Nah, this is no. You know what? I don't need to make methods for all these. Get pixels from the intersection between the two of them. Crap, this is frustrating. I have 4 cases. Okay. I think what we're going... shoot. This is more troubling than I thought. I was really hoping I could get this done today. Because it's such a simple issue. I keep trying to avoid cases, but I'm going to have to. So I don't think I'm going to do this. We're just going to comment it out. I will have a width difference and I will have a height difference. We don't really need this intersection. I don't think we need that. If image 1 dot width is bigger than image 2 dot width, let's say if image 1 dot width is bigger than image 2 dot width, then min width equals image. See, this is exactly what I solved up here. Smaller width and smaller height, so that's fine. That's the size. Intersection, this is the size. Here we go. But it's not the size though, that's the issue. We're not finding the size, we're finding the offset. Okay, let's just... Oh, wait a second. Okay, so... because I want to count them both. Okay, guys, let's... I think it's my for loops that are the problem. Let's just start with the bigger image. So, for x... Come on. We're going to start off at 0. X is less than the one with the bigger width dot width. Okay, and we'll do that. And then we'll go for int y equals 0. y is less than bigger height dot height y plus plus. Okay. This will count the entire image. So I'm going to say, so this will look at every pixel in the giant canvas that contains both of them. Okay. We're not going to move anything around. We're just going to stay where we are. Okay, so then I'm going to say if x is less than image1 dot. Well, first let's do this. If x is outside the bounds of image1 dot width and x is outside the bounds of image2 dot width, that'll never happen. So if we're outside the bounds of image 1, okay, here we go. Probability equals 0. Up here, we we'll do it in here. We're going to have a few constants. Match value equals 1. And then we'll say unmatched value equals 1. And we'll tweak these as necessary. So if the pixels match, we'll use the matched value. If they don't match, we'll use the unmatched value. So if x is greater than the width of the image, we're going to go probability unmatched value, because that means we're within the width of image 2, but not in image 1, so they don't match. Oh, but actually, let's just, or x is greater than image 2 dot width. So if we're outside the bounds of one of the images, then they're not matched. Let's say actually we need to because in the case of this, down in this corner, they both don't have anything. So we don't actually want to count that. So that's the case when the width and the, yeah, so, okay. We really don't want to count that. So let's say, okay, if x is greater than image1 dot width and y is greater you know what, we're just gonna say image 1 has pixel image 1 xy, image 2 has pixel pixel, come on, image 2, x, y. And then if image 1 has pixel and image, so if image 1 doesn't have the pixel and image 2 doesn't have the pixel, then we're unmatched on both counts. We don't want to add anything. So I don't have anything to add. What am I putting that in an if statement for? If image 1 has pixel and image 2 does not have pixel, then we are going to add to the probability an unmatched value. Okay. Otherwise, if image 1 you know what we can do? We can use the XOR operator. What is that? Let's get fancy here. The exclusive OR operator will be true when exactly one of the two sides is true. Logical exclusive OR is the caret. Okay, it's the caret. So image 1 exclusive OR image 2. So this is, one of them has it, but they both don't have it. Then we're going to just say unmatched value. And then we're going to say else if image 1 has pixel and image 2 has pixel, then we're going to see if they're the same. Then we're going to see if they are the same. Do I have an isBlack method in here? Yeah. If image 1 dot get pixel at xy is black, and is black, well, you know what, bar image 1 pixel is black equals is black image 1 get pixel xy image 2 pixel is black is black. Here we go. We're gonna get there eventually. Okay. And then if image 1 pixel is black equals image 2 pixel is black, then we're going to say probability plus equals unmatched value, not unmatched value, matched. What's the problem? Matched value. I should make this -1 because I'm always adding. If they're not equal, then probability is going to get added to it, the unmatched value. There we go. And then, what is going on? What do you mean expected? Looks fine there. What? Okay, I need to make this method, but what's the problem? What's the problem here? Expected. What? If I put a semicolon there, that's gonna freak out. Oh, that doesn't make any sense. Can I rebuild my solution? Sometimes Visual Studio does this, and it's terribly bothersome. Oh man, is it late already? What the heck is wrong? That's fine. Man, syntax errors really stink. Oh, my bad. It's an else if. Else's don't have conditions. Okay. Yeah. So there we go. Now I just need to find as pixel on the image. So return x is less than. Now, pixels go from 0 to the width minus 1. So if the width is 40, x has to be 39 or less. So x is less than image1 dot width. And y is less than image1 dot height. Okay. So this will give that to us. And this will just do one pass. And then I want to start moving them around, but that's going to require this whole for loop here is one pass. And then I have to start moving them. So I think, yeah, I'm going to have to stop it here. I don't want to wait another week though, because I'm really close. So we'll stop it here. And I want to come back to this soon, but I got to do some things, as always, because I have a life most of the time. So, okay. Thanks for joining me. I'll see you next time.